అట్లా అంటున్నారు.
అంటున్నారు కానీ గంట అయింది స్పీచ్ కదా.
అడిగాను రెండు మంచాలని అని ఇంగ్లీష్ ఏదో ఆడదామని మాట్లాడుకొని అప్పుడు వాళ్ళు చెప్పారు వాళ్ళు చేస్తున్నారు కాబట్టి వాళ్ళని కొంచెం
Welcome, Principal K.S. Bose Garu.
Thank you, sir.
Sir, good evening.
Good evening,
Yeah.
Master. Good evening, Master.
Principal garu, good evening.
Good evening and good evening.
We will wait another few seconds. In the meantime, Dr. P. Anil Kumar Garu, Chief Guest of our FDP session, will join.
Sir, good evening, all of you. I have joined, sir.
Good evening, sir. Good evening, everyone. Myself, Professor G.R. Smurthy, coordinator of this FDP. Respected management members, Director R&D, Professor P.V. Sharma Garu, Dr. P. Anil Kumar Garu, Principal APCHI, Dr. K.S. Bose Garu, Director, Principal GVPCD PGC, Technical Director, Dr. P.V. Vinay, eminent persons from NITs and IITs, experts in quantum computing, and all the beloved participants across the India. Good evening to everyone. A warm welcome to 5 days ATAL online FDP on quantum computing with artificial intelligence, convergence and applications. The FDP is not just another program. It is a golden opportunity for all of us to gain competitive edge in our academic and research careers, become pioneers in the domain that is going to define the future of the technology. At the same time, this FDP empower our students with cutting edge knowledge and prepare them for the jobs of future. The central government national mission on quantum computing, at the same time, the state government Amaravati Quantum Valley, both focuses on emerging technologies, which reflects the national and state level commitment to foster expertise in quantum computing. Faculty who can take an early lead in this domain will not only advance their careers, but also play a pivotal role in shaping the future of our students and the future of our nation. As educators, we are the bridge between knowledge and innovation. Our role is critical in inspiring the students to explore quantum computing, developing a curriculum that integrates quantum principles, and at the same time collaborating with industry and research institutions to drive innovations. I urge each one of us to seize and use this opportunity, learn from our eminent resource persons, engage with industry experts, and take back insights that will transform our teaching and research. Over the next 5 days, all of us will hear from 4 distinguished resource persons from NITs and IITs, followed by fruitful sessions from industry leaders who are working actively in the quantum computing. This blend of academic rigor and industry relevance will give us a holistic understanding of quantum computing and its application. As we begin this FDP, I leave you with a thought. The future belongs to those who prepare for it today itself. With this, I will request Professor P.S. Bose garu to give his valuable speech.
Thank you, Professor G.R.S. Murthy garu. This is Professor K.S. Bose, Principal Gayatri Vidya Parishad College for Degree and PG courses at Autonomous Visakhapatnam. I am very honored to welcome all the guests and participants for this very valuable inaugural session of 5-day ATAL FDP on quantum computing and artificial intelligence, convergence and application scheduled between 25th August to 30th August 2025. Respected Chief Guest, Dr. P. Anil Kumar Garu, Principal, APSHI, my teacher, Professor P.V. Sharma Garu, Member, Gayatri Vidya Parishad, Professor D. Kameshwarrao Garu, Member, Gayatri Vidya Parishad, my friend, Professor P.V. Vinay, Director, Engineering and Technology Programs, Gayatri Vidya Parishad College for Degree and PhD courses, Autonomous, and the coordinator of this entire program, Dr. G.R.S. Murthy Garu, and co-coordinator of this program, Dr. D.S.S.N. Raju, eminent resource persons from NITs, IITs, and different institutions across India, industry experts in quantum computing, and all the beloved participants from various places located in India. I am particularly delighted to see that there are around 450 participants are registered for this FDP on quantum computing. Both our central and state governments are supporting various FDPs on quantum computing. The state of Andhra Pradesh has always been at the forefront of education and technological innovation. By mastering quantum computing, you can contribute to the making India and particularly Andhra Pradesh a hub of quantum research and development. At the end, once again, I congratulate the coordinators of this program, Professor G.R.S. Murthy and co-coordinator Dr. D.S.S.N. Raju for organizing this FTP in more systematic and well-structured manner, and wishing you all to take part actively in this program, and I hope this program will enhance the knowledge and skill in quantum computing for all participants here. I wish you all the best for participants and organizing, and I thank you all for making me the part of this event today evening. Thank you, sir.
Thank you, sir. Thank you very much for your words. Now I request Director Engineering, Professor P. Vinay sir, please to speak a few words. Vinay sir, are you there?
No, sir, maybe he's not there. Sir.
Give me 1 minute. Let me check.
చెప్పు హలో
Sir, Arun sir, please turn off view for Vinay sir. I think mistakenly we make him as a viewer. That's why he is not, I am unable to see him. Sure, చెప్పండి. లేదు Sorry for the inconvenience. In the meantime, may I request our management member, Sri Rameshwar Garu, to say a few words. Sri Kameswar Garu.
సార్ జిఆర్ఎస్ సార్ ఒక్క నిమిషం ఉండండి సార్ జిఆర్ఎస్ మూర్తి గారు
Ma'am,
కామేశ్వరరావు గారిది మైక్ను కెమెరా ఆన్ అవ్వట్లేదు అంటున్నారు
ఒకసారి చెక్ చేస్తున్నాం మ్యామ్. గివ్ మీ 1 minute.
చేయండి ప్లీజ్
Sir, ma'am, now Professor Kameswar Garu can speak, ma'am. Can I request Sri Kameswar Garu to speak a few words?
Hello.
Yeah, sir.
Am
Good
I
evening,
audible?
sir. Yes, sir, you are audible.
Thank you very much. I have very well. Good morning to all the respected audience and our chief guest, Anil Kumar Saab, and other distinguished professors and veterans in the subject. And I congratulate the organizers first for having taken up this great session. And I am sure all the participants, not only our faculty, but faculty from other colleges of this region, have a benefit of this participation of the sessions and retain their knowledge. So I expect all of them to be very particularly concentrate on the sessions and learn a lot. Tomorrow, they will be the trainers for our trainees. I wish them all success. And once again, thanks the chief guest for having taken the time to come over here, and our other participants also, on behalf of Gayatri Vidya Parishad and on my behalf. Thank you very much, sir. Hello? Hello? Murthy garu?
Thank you, sir. Thank you very much.
Thank you, sir.
Thank you, sir. Now, may I request Chaganti Gopika, ma'am, who is from Quantum AI Industry Research Director, to speak a few words. Ma'am, are you there?
Yes, am I audible?
Yeah, you are audible, ma'am.
Yes, thank you so much. At the outset, I would briefing to the chief guest part of this wonderful inaugural function that is happening today. It's an initiative that is state of the art. I would like to congratulate Gayatri Vidya Parishad and the efforts of most of our all together here. I just wanted to give a brief about the landscape of quantum and why it is important for us. When you think of a nation, the essence of a nation is the knowledge base that a nation has in terms of how we are equipped with the cutting edge technologies or advancements in various fields. If you have seen, the technology has been improving since last few decades, and India as a nation did miss few buses when it comes to industrial revolution, semiconductor revolution, and also, unfortunately, a little bit of AI initially, but I think that's picking up there. But the prospect to win quantum revolution is still in our hands, even though the national funding for it is low, which is 0.7 billion, and China is standing on the top. We are still in the top 10 who are actively pioneering and initiating quantum technologies when it comes to various fields which are sensitive in terms of defense, finance, and telecommunication. As we know, National Quantum Mission, we have 6,000 crores of funding, and there are 4 verticals of quantum technology, which is communication, sensing, medical devices. This specific ATAL initiative for faculty development program is focused on quantum computing and AI, which is the next generation modality. Why? Because AI today is super quick, super fast in terms of software, in terms of GPUs, in terms of acceleration. But where do we hit a wall? We hit a wall in terms of the hardware. That is where a quantum computer can do. I would like to remind each one of you that quantum technologies, quantum computing will work with classical computing. Quantum computing is very good with specific problems, and artificial intelligence will accelerate the performance of those problems in terms of optimization, in terms of speed, in terms of communication. Thank you so much for giving me this opportunity as an industry partner. I thank even my company, Quantum AI Global, for which I'm representing in this session. I wish all the participants a successful knowledge, learning, and sharing.
Thank you, ma'am. Thank you, Gopika ma'am. Now I request our chief guest, Principal Apchi, Dr.
Thank you, sir. Thank you for inviting me.
Speak. Thank you, sir.
Am I audible, sir?
Yes, sir, you are audible.
So, good evening, all of you. It's really a great initiative by Gayatri Vidya Parishad in collaboration with ATL and National Quantum Mission and DST, and also in collaboration with the AICT initiative. So this 5 days definitely will give our faculty wings to rise up to the mark of this cutting edge technology, particularly the quantum computing and artificial intelligence, convergence and its applications. As the title itself is aptly designed, definitely it will inspire all the faculty members, maybe across AP, more than 250 faculty are joining here, and the rest from the all over India. It is a very relevant subject and relevant topic. First of all, I appreciate the management of Gayatri Vidya Parishad, the faculty, the principal, the coordinator, and other members who are actively involved in this, particularly Principal Professor K.S. Bose Garu and Vinay Garu, Coordinator, Director, Dr. G.R.S. Murthy Garu, and Dr. D.S.S.N. Raj Garu. And when I see this brochure, there is a galaxy of resource persons across India. Of course, Srinijoy Ganguly is from London, Dr. P.V. Subba Reddy Garu, NIT Warangal, Professor Naresh Kumar Garu, NIT Raipur, Professor Dabajyoti Bera, IIT Delhi, Dr. Kapil Kumar Soni, NIT Raipur, Dr. Gopika Chaganti, Quantum Global Hyderabad, Dr. Shalini D, Haryana, and Dr. Aniruddha Biswas, Kolkata, Professor Gangopaja, IIT Roorkee, Dr. R.S. Jordan. So all these very eminent personalities, they're going to deliver the talk. And the topics chosen are also very well stitched in, for example, starting from fundamentals to the future directions and challenges in quantum and as well as AI. I would like to congratulate once again. Parallelly, I thank Professor K. Madhumurthy Garu, Chairperson of AP State Council of Higher Education, for his initiatives. We have designed the curriculum for major courses in quantum as well as majors in artificial intelligence. We also designed the curriculum for minor subjects for minors in quantum as well as artificial intelligence. The AP State Council Higher Education vision is to deliver the goods to every citizen, every student across Andhra Pradesh. Whether he comes from engineering background or whether he belongs to physics, computer science, mathematics, we are not leaving the life sciences faculty as well as the faculty from humanities and social sciences, because it is itself, the subject is a multidisciplinary one. We are including even from economics, even from commerce, because there are so many issues like fraud, finance management, and also there are applications in what you call handling logistics, etc. So due to this, we have given equal opportunity for all the faculty across the different subjects. Maybe it includes core engineering or sciences or even arts like commerce as well as economics. Because due to the nature of its multidisciplinarity, we are engaging everybody. Not only that, parallelly, we are also supporting student community. So at one time, we are going for course designing, and parallelly we are going for faculty development. Now, in collaboration with the DST, MIT, as well as IIT Madras, MIT Jaipur, and other national quantum missions, in a collaborative approach, we are almost training more than 1,000 faculty members. The first module is already commenced, and it goes up to March and April 2026. Why we are going in parallelly for all this? Apart from this faculty development, or apart from this designing of the curriculum, we have also submitted 84 proposals for quantum algorithms to DST and QM, and almost 134 proposals for quantum UZ teaching labs across AP. So this is one of the highest figure from any state, because we are parallelly looking into the hands-on experience. Without the quantum labs, we cannot go for this. Not only that, we are also going for application part where we have submitted almost 84 algorithms to the DST. Parallelly, we are also hand-holding student community. Recently, with the 20,000 students, we have conducted a boot camp on this quantum technologies, and very shortly we are going to arrange an internal hackathon across India. Other than AP, we have invited so many students from other states also. Some students from Maharashtra, some from Tamil Nadu, some students from even Punjab, Haryana, Himachal Pradesh, Karnataka, Telangana. They are also participating in this hackathon, Amravati Quantum Valley Hackathon. This is one of the prestigious, and even the resource persons who are involved, the scientists who are involved in IBM, TCS, etc., they're also collaborating with us. Not only that, we are also involving the startups also. Many startups are also involved in this. So to my surprise, most of the students are very excited to involve in this quantum technologies, because this is a urgent need. By 1/1/2026, as per our Honorable CM, Sri Nara Chandrababu Naidu vision, 156 qubit IBM machine is coming to Amravati. Already, most of you know that the work is already commenced. The L&T is working on this physical infrastructure, whereas both TCS and IBM, the main mission will be coming from IBM mission 156 qubit. Not only this, there are so many startups are coming around Amravati Quantum Valley, and even QPI from Bangalore is also establishing one 8 qubit mission. So there are so many opportunities, whether it is jobs or startups or so many applications are there. Due to this multidisciplinary nature, there is a huge demand. So as per our APSHA chairperson vision also, Professor K. Madhumurthy Garu visualizes that at least we have to produce 1,000 faculty. I'm happy that even the Gayatri Vidya Parishad, there are more than 525 faculty members are attending this workshop. And 5 day, 6 day, I think 5 day faculty development program on quantum computing as well as artificial intelligence. Definitely it will lead to, it will make Gayatri Vidya Parishad and even our state also, with this empowerment, the faculty must be a game changer contribution to this IBM quantum mission whenever it is established, going to establish 1/1/2026. The work is going on very fast pacing. In this connection, I think Gayatri Vijaya Parishad is doing a marvelous faculty development program. I wish you all good luck, sir, the management, faculty, and all the stakeholders, the extraordinary, excellent resource persons across India, and of course, from London, one resource person joining. I thank profusely on behalf of APSHA also. I thank the organizers. Thank you very much for giving this opportunity. Thank you very much, sir.
Thank you, Dr. P. Anil Kumar, sir, Principal APSHA, for your valuable words. We definitely support and take part in the Quantum Valley, Amravati Quantum Valley participation. GVP from its side definitely will participate, sir. Thank you, sir.
Sir, one more request from my side, because being the Gayatri Vijaya Parishad is the semi-final spot for this hackathon.
Yes, sir.
Kindly give more publicity so that more and more students can join at your place for the semi-finals, and also definitely see that some use cases also will be generated by the end of the hackathon at your place. This is our concern, sir. This is our
Definitely,
vision.
sir.
Thank you.
We will do it, sir. Thank you, sir. Thank you very much for joining, sir.
Thank you, sir. Thank you, Anil Kumar, sir. Thank you very much.
May I request Professor Vinay, sir?
Can you say a few words, Anil Kumar sir?
Sir, I think he has gone.
Yes, sir. Yes.
Okay.
Yeah, he's there.
I just want to profoundly thank him once again for his kind words about Gayatri Vijaya Parishad, and definitely we'll do our best.
Sir, our chairperson, Professor K. Madhumurthy Garu, selected your institution because of your all-round development, your quality aspects, and all the facilities you have. Whether it is infrastructure-wise or human resource, everything you have. That's why our chairmen are selected your institution.
Thank you very much, sir. Thank you very much. It's because of all blessings from people like you, either in the government or university or the public at large.
Thank you.
We'll definitely come up to your expectation. We strive for it, sir. Thank you very much.
Thank you.
May I now request Professor Vinay, sir, to say a few words? I think he has.
Thank you so much, Murthy Garu. Am I audible?
Yes, sir, you are audible.
Yeah, sorry for being a little tricky with my fingers. I could not log in a little early. Then again, it's a nice effort that Dr. GRS Murthy and Dr. DSS and Raju had done. Hope majority of the people would take advantage, being the starting people who would jump onto this bandwagon, because this is going to create a huge opportunity for people to work on, as well as analyze and give a correct amount of output. With artificial intelligence, it's going to be an advantage again. So hope everybody learns good. These 5 days are going to create springboard for everybody to jump onto this quantum computing. And with the push that the government as well as different colleges and institutions are giving for quantum, hope everybody would have good opportunities and they excel in whatever they have learned. Thank you so much, Murthy Garu. Thank you so much, everybody, for being here. Thank you very much.
Thank you, sir. Thank you very much for all of you joining. Now I request my co-coordinator, Dr. DSSN Rajagaru, to propose final vote of thanks.
Sir, good evening, one and all. I am Dr. DSSN Raju, co-coordinator of this FDP, that is Quantum Computing with Artificial Intelligence, Convergence and Application. It is my privilege to deliver the vote of thanks for this 5-day faculty development program of Quantum Computing with Artificial Intelligence, Convergence and Applications. I extend my heartfelt gratitude to Dr. P. Anil Kumar Garu for gracing this occasion as our chief guest. Sri DBS Kameswar Rao Garu, Joint Secretary, Gayatri Vidya Parishad. Professor K.S. Bose Garu, Principal, Gayatri Vidya Parishad College for Degree and PG courses. Professor P.V. Venay Garu, Director, Engineering and Technology Program, for their consent, support and visionary leadership. The distinguished resource persons and industry experts for share their valuable expertise. This 5-day FDP is unique opportunity for us to enhance our knowledge, exchange ideas, and gain deeper insights into the emerging field of quantum computing. Let us engage with enthusiasm and determination. I wish all the participants a productive, enriching, and intellectually stimulating 5 days of learning. Thank you all. Thank you, G.R.S. Murthy sir, coordinator of this program.
Thank you, sir. Now we conclude the inaugural session. Now I request Professor P. Subba Reddy Garu to start his first session on this quantum computing. Sir, am I audible?
Yes, sir. Yes, sir.
Sir, now Professor Subba Reddy Garu is from NIT Warangal, a eminent sports faculty who has vast experience in teaching quantum. Now I request Professor Subba Reddy Garu to share his screen and start the session 1 of the today. Sir, now you can take the control.
Thank you very much, sir. First of all, I would like to thank the coordinators and the administration for giving me an opportunity to be part of this FDP. So now I'm going to share my screen. Sir, is my screen visible to one of you? Please respond.
Yes, sir, your screen is visible.
Okay, okay. So I try to make the lecture as self-contained as possible without making any assumptions about your knowledge in quantum computing. Okay, if you have any doubts at any point of time, you can interrupt me and ask me. Okay. So in the first session, we are going to learn what is quantum computing and what is the need for quantum computing and what are fundamentals of quantum computing. Okay. So we'll try to make it interactive. Okay. So those who want to respond, I think with the permission of coordinator, I request them to please unmute yourself and respond. Okay. So So whenever we say problem, do we consider this type of problems as problems in engineering or science for that matter? How to become rich in 2 years? Do you want some computers or computing devices to solve this kind of problems? Sir, coordinator, sir?
Yes, sir.
Yes, can participants unmute and respond, sir? Do they have that option?
We are giving, sir.
Okay, okay.
Yes, sir, we are having the option, sir.
Okay, okay, okay.
Thank you.
Thank you, sir.
Yes, madam. When you need, you can unmute and talk, ma'am.
Okay. So do we consider this type of problems, how to become rich in 2 years or how to remain happy forever? Do we consider this type of problems? Whenever we say problem, do we actually consider this type of problems?
Not exactly.
No. Why? What is the reason here? So, okay, whether we consider this type of problem, whenever we say problem, determine whether given natural number is prime or not. So what all of us know what is a prime number? A natural number n greater than or equal to with 1 and itself as divisors. No other divisors. For example, 6, is it a prime number? Is it a prime number?
No.
No.
No, sir, no.
No, 6
No,
is
sir.
not a prime number. But we know that 7 is a prime number. Why? Because 1 and 7, these are the only divisors of 7. No other divisor. Hence, 7 is a prime number. Now, have you heard, all of us must have heard about prime factorization. Okay, what is prime factorization of a number? We know what is a prime number. What is prime factorization? So before understanding that, we try to understand what is integer factorization. So integer factorization is very simple. We are given a number, natural number 6. Okay, is it a prime number or not? Is 6 a prime number or not? No. We are given a natural number 6. We need to write it as product of its divisors. Product of its divisors. So can we write 6 as 2 into 3? If 12 is given, how to write 12 as product of sum of its divisors?
2 into 6.
2 into 6. 2 into 6. For example, 24 is given. We can write it as 2 into 6 into 2. Is that okay? Given a natural number, writing it as product of its sum of its divisors or factors. It is known as integer factorization. For example, what are factors of 36? Can someone tell me what are factors of 36? What are factors of 36? Okay. All of us agree that these are the factors of 36, no? 1, 2, 3, 4, 5 is not a factor. We know that. So these are factors of 36. Now, 36, is it possible to write it as 1 into 36? Or 2 into 18? 3 into 12? All are correct, no? Their product is nothing but 36. This is called integer factorization. This is called integer factorization. Given natural number, in this case 36, we are able to write it as product of sum of its factors, some or all of its factors. Now, in this case, if you look at last one, 2, 2, 3, 3. Here, all factors are prime numbers or not. Is 2 a prime number? Yes. Is 3 a prime number? Yes, all factors are prime. So we have written 36 as product of 2, 2, 3, 3. Yes, product of its factors where all factors are prime numbers. Where all factors are prime numbers. Is that okay? And this kind of factorization, integer factorization, it is a special case and it is called prime factorization, where every factor is a prime number. Can you give prime factorization of 6? What is prime factorization of 6? What is prime factorization of 6?
2 into 3.
2 into 3. Similarly, can you give prime factorization of 24? Here 2 is a prime, 3 is also prime. Hence it is correct. 24.
2 into 6 into 2. 2
Ah,
into 6.
this is not correct. Why?
Yes.
Because here 6 is a factor, but which is not a prime number, no? This is only factor, integer factorization, but not prime factorization.
2 into 3 into 2 into 2.
Thank you very much. 2 into 3 into 2 into 2. This is here 2 is prime, 3 is prime, 2 is prime, 2 is prime. Okay. This is called prime factorization. Is the problem clear? What is prime factorization? It is a special case of integer factorization where every factor is a prime number. Where every factor is a prime number. Now can you find out what is prime factorization of? But this prime factorization, given a number, natural number greater than or equal to, this prime factorization is unique, except for reordering the terms. Okay, now instead of writing 2 into 2, 3 into 2, we may write it as 2 into 3 into 2 into 3. This is only reordering the factors. Except for this fact, this prime factorization is unique. Can you try to give any other prime factorization of 36? Any other prime factorization of 36?
Yeah. 2 into 3 into 2 into 3 into.
2 into 3 into, but it is same as 2 into 2, 2 into 3 into 3, no sir. It is only reordering the terms, no, that's all. So except for this part, reordering the terms, this prime factorization is unique. For a given number, there is only one prime factorization. Is that okay? So for example, 504 you take, this is prime factorization. Where all are prime numbers. We can short form, we can write it like this also. This is prime factorization. Now we talk about 4 problems. What are they? How to become rich in 2 years? How to remain happy forever? Now, is there any calculation or computation in these 2 problems which computers can do? No, there is no calculation or no operation we are performing here. So this type of problems, no, we say that they are not computational problems. They are not computational problems. We are not interested in this type of problems. But here, prime number or not, is there a computation or calculation? Yes. What is that we need to do? We need to find, is 1 anyhow, we know that it is a divisor or factor. Is 2 divisor of that number or not? Is 3 divisor of that number or not? If, for example, 8 is given, is 4 divisor of that number or not? Is 7 divisor of that number or not? All these things we need to do. If there is no divisor other than 1 and 8, we say that it is prime. Otherwise, we say that it is not prime. Is that okay? There is some calculation. Even here also there is some calculation. And this type of, there is some computation. These type of problems are called computational problems. Whenever we say problem, okay, no? So we mean computational problems. There is some calculation or computation involved in it. Okay, that type of problems. So 3 and 4, these are computational problems. Now, then what is a computational problem? So it is a problem. Hereafter, we use computational problem means problem only. Whenever I say problem, we need to understand it as computational problem only. Okay, it is a problem that computers might be able to solve. Okay. So whether computers can solve this problem? Yes. Whether computers can solve this problem? Yes. Okay. So can you give any other example for computational problem? Any other example for computational problem?
Factorial of a number.
Sir? Any other example for computational problem? Okay, sorting problem. That is a computational problem. Okay. Next, now we have a problem. Problem means computational problem. So then what does computing mean? What does computing mean? So in order to find solution to this, definitely we have to perform some calculations. That means some computation or some operations we need to perform. Some operations we need to perform. We are given a computational problem. That means there is some calculation or computation involved in it. Then what is computing? What is computing? It is we are given a problem, computational problem, and we want some computing devices like computers to solve it that problem for us. To solve that problem for us. Okay. Now this computing involves what? It involves hardware. It also involves software. So for example, if you take normal, we have a problem, sorting problem. Okay. So we have computer, that is hardware part. We write a program for that in some language, C++ or Python, some language. That is software part. Now we give some input, and that processes that input inside that CPU. It processes that information. That means that algorithm we write that processes that information. It gives output. Okay. This computing involves hardware as well as software. Is that okay? Computing involves hardware as well as software. Okay. Now, what are different types of computing? These are different types of computing. Those who are from computer science background, you must have done some courses out of this also. Others, at least you might have heard these terms. Okay. There are different. So finally, we have a problem. We need to solve that problem. Okay. So for that, there are different types of computing. So in that, we are interested in this way of approaching or solving the problem. That is quantum computing. So computing involves hardware as well as software. Then what is quantum computing? We know what is computing. Then what is quantum computing? What is quantum computing? It is a type of computing. But what is special about this computing? What is special about this computing? It uses the principles of quantum mechanics to process the information. Okay. Then what is quantum mechanics? All of you might have, definitely you might have heard about quantum mechanics. What is quantum mechanics? It's a branch of physics. All of you agree? It's a branch of physics. Okay. But what is that? What is that? It is a branch of physics which deals with the particles at the smallest possible level. That is atomic as well as subatomic level. Okay. What is smallest possible level means? Atomic, subatomic level means it is at what is smallest possible level for that? Electrons, neutron, photons. So, okay, these are smallest possible levels. Okay. Next, what are the principles of quantum mechanics? What are main principles of quantum mechanics? There are many principles of quantum mechanics. So mainly these are some principles of quantum mechanics. Out of that, we are going to talk mainly about these two principles. So more informally, this is not the correct definition what I am giving, but you can usually understand this. What does it mean using this definition? I repeat, it is not the correct definition, but it is only to understand the concept better. Okay. Now, if I toss a coin, we have tossed a coin. Now, when the coin is rotating, what is the state of this coin? Can you exactly tell what is the state of this coin?
Head or tail?
But that we exactly don't know, no, sir. It may be heads or tails combination, no?
Yeah.
Standing position. Sir, when it is rotating, it may have different chances.
Different. So heads also possible, tails also possible. Okay. Exactly, we don't know what state it is in. But once it falls on ground, we see, okay, this side, if you see, we say that it is in head state. If we see it like this, we say that it is in tail state. Is that okay? Now, when it is rotating, we can imagine like it is combination of both states. Some part in heads, some parts in tail state. Is that okay? That is, coin, there are two possible states, heads and tails. When it is rotating, it is going to be combination of both states, okay? Both states. Some part of it in one possibility, some part in other possibility, but both it is present. And this kind of existing in multiple states at the same time, multiple possible states at the same time, it is called superposition. But it is not, because coin itself, it is not the correct example. Okay, that later you will understand. Okay. So now is it clear? What does superposition mean? More formally, we will discuss after some time. What is superposition? Existing in system, existing in multiple states, multiple possible states at the same time. Okay. Is this point clear at least? Up to this?
Yes, sir.
Yes, sir. Yes, sir. Clear.
Okay. Until it is measured means it is falling on ground. That time there is no superposition. We see either heads or tails, one only. Until it is measured, this is important. Measuring means now you can understand like it is rotating. It has not fallen on ground. Okay. Next one is, to be more precise, this is an exact electron. It can exist in different energy levels at the same time. So different possibilities, it can exist in multiple possibilities at the same time. So that is exactly the definition of superposition. But more formally, we will discuss after some time. Okay. Then, okay, well, the next property, most important property is, let us say, these are twins. In mythological movies, or you might have heard people saying that this is baby girl, girl 1, girl 2. This girl is in, say, in Amaravati. The other girl is in London. Okay. The other girl is in London. So you might have heard like twins, they share some special properties. If this girl smiles, all of a sudden, because here distance is more. One is in Amaravati, the other girl is in London. Okay. All of a sudden, this girl also starts smiling, irrespective of the physical distance between them. If this girl cries, all of a sudden, this immediately, instantaneously, this girl also starts crying. That means G1, it is instantaneously, it is going to affect the state of G2, no? Now, can we say, for example, one is on Earth, let us say one girl is in Vizag, okay, Vizag. The other girl is in Mars. Okay, now assume that Elon Musk SpaceX that becomes successful in future, people may go to Mars. Like how do we go to different countries now? Okay, one is in Vizag, the other girl is in Mars. If this girl smiles, who is in Vizag, automatically the other girl who is on the Mars starts smiling. Yeah, this distance is very long distance. Still, one is affecting the other. then we say that these two are not independent, though we have physically separated them, okay, no, with long distance, but still they share something in common. There is some kind of relation or correlation between the two. And this kind of thing that we call it as entanglement. That means you can understand it like they are not independent, irrespective of the physical distance between them. If you make something here, something else is going to happen in the other side. Is this okay? Entanglement means at least they are not independent. At least that point, is it clear?
Yes, sir. Yes, sir.
If some changes happen here, automatically, instantaneously, other changes are going to happen irrespective of the physical distance between them. Okay. So similarly, there are other properties which we may not directly use. Hence, I am not going into details of that. Okay. Next question is, so those who you might have seen this kind of pictures, no, when our quantum computer people display either in newspaper or, okay. This is the commonly used diagram. Now, as of December 2023, this frontier computer, this is considered as the fastest computer in the world. It was in the year 2023, December. Okay. This frontier. But later, November 2024, this has taken over. L-Captain. Okay. This is considered as the fastest supercomputer in the world. Okay. The fastest supercomputer in the world. Now the question is, we have so powerful supercomputers, then why are we talking about this computing which is based on principles of quantum mechanics, that is quantum computing? Why are we talking about this quantum computing? Okay, if we have powerful supercomputers, then why there is so much hype for this computing? There must be some reason. That is, there are some problems which, even if you take this fastest supercomputers available, they are not able to solve them in reasonable amount of time. This fastest supercomputer also. But this quantum computers, if they become reality, already small size quantum computers are available. Okay, then they can solve those problems in no time. That means, what does it mean? There are some computational problems or problems which the fastest computers available today, that is supercomputers, they are not able to solve. But this quantum computers based on this quantum computing, based on, if these quantum computers become reality, they are going to solve those problems in no time. Let us see with an example. Okay. Now all of us know what is integer factorization problem. Okay. Now let us talk about this integer factorization problem again. If we are given 6, directly we can say 2 into 3. If we are given a large number, these personal computers or our laptops, they take very, very long time, astronomically long years, crores of years of time. That means practically it is impossible to find integer factorization of a number on personal computers for large values of input. Is that point clear? We know what is integer factorization problem. Given a number, we need to write it as product of its factors. Okay, no, product of its factors. Okay. But if input n value is more large value, on personal computers, they take crores of years. Instead of that, if you use supercomputers, how much time do you think they take? How much time do you think these supercomputers take? Any answer?
Milliseconds, sir.
No, sir. It is not as expected. Many of us actually expect that the supercomputers can solve in less time. They also take hundreds of years. This integer factorization problem, appears to be very simple, But if n value is large, it is going to take a lot of time using the fastest computers available today. But if you go for this quantum computer, how much time do you think they take? How much time do you think they take?
Very less time, sir.
They can solve it in minutes to hours. Okay, sometimes even seconds also. Okay, is that okay? So that means now we know that integer factorization problem on classical computers. These two are based on classical computing, no classical computers. They take a lot of time. But if I use quantum computer, in no time, in seconds to minutes or hours, we are going to get answer. This is one such example. This is one example. Next question is, so what? If quantum computers can solve integer factorization problem quickly, what is that we are going to lose or gain? There should be something, no? Are you following? We are trying to understand why quantum computing is required.
Yes, sir. Yes, sir.
Okay. Now, integer factorization problem, classical computers, they are not able to solve in reasonable amount of time. Reasonable means, in more formally, we say that polynomial amount of time. But this quantum computers, they solve it in more time. No time. Okay. Now we have understood that there is a problem, at least one problem, which supercomputers also they are not able to solve. But this quantum computers can solve it in very less time. Very less time. Then what? That means this quantum computers can solve some problems very easily than this classical computers. No, that much is clear. That is okay, fine. Then what is the advantage that we get? What is the advantage we get? That is important, no? That is important. Next one. Let us say we are given an integer n, and we need to write it as product of two primes p and q. That means n should be equals to p and q, where p is a prime and q is also prime. Input is n. What is output? Two prime numbers p and q, such that n equals to p into q. N equals to p into q. P times q. Is the problem clear? Is it possible to solve this problem easily? Is it possible to, classically I'm asking, is it possible to solve this problem easily? Easily means polynomial time.
It is difficult, sir.
Is it possible to solve this easily?
No.
No. Classically, no efficient algorithm is there. Okay, no, classically. But whether quantum computers can do it easily? Yes.
Yes, sir. Yes, sir.
Yes, sir. Quantum computers. Okay, no, that I will tell you the name of that algorithm. Okay, they can solve this problem easily. There are some problems. Okay. Now, next question is there a problem where quantum computers can solve very much faster than classical computers? Yes, we have seen one example, no? Integer factorization problem. Integer factorization problem. Now, there is a quantum algorithm for that. Quantum algorithm called source algorithm, which easily solves that, which solves in polynomial amount of time. That means, given n, we can find p and q, where p and q are prime numbers, in polynomial time easily. In polynomial time easily. That is, next question. Is there a problem where classical computers, they take more time? More means non-polynomial time. But quantum computers, they do it in polynomial time. Yes. Again, the example is integer factorization problem. Integer factorization problem. These three questions is answer clear? Classically, no. Classically, no. Quantum, yes. Madam, any doubt?
Yes, I have a question, sir. Actually, we did these problems in our school time.
or we can say that in our +1, +2 timings. But that times, I think there were no quantum computers. But but that time we can tell that this is a solvable problem. So how can we tell that time it's a solvable problem? It's not.
Yes, ma'am. Your point is correct. That is solvable means we can find it by, but it takes more time. It takes more time. It is not that it is impossible to solve. No, it takes more time. But the question is, but question is, we want answer for that problem in less time so that we can use that answer to do something.
Okay.
Otherwise, it is of no use, madam.
Okay, that means quantum computing is only for reducing the time.
Here I am giving you an example where quantum computers can solve the problem very easily. But classical computers, they take a lot of time. It is impossible to solve efficiently.
Okay, that means there is known polynomial solutions were there, right?
Is this slide clear, madam? This, I think it might.
Yes. Thank you, sir. Thank you so much.
Okay, madam. Okay. Next question is, okay, now by using quantum computers, we are able to find, given n, we are able to find two prime numbers p and q such that n equals to p and q. So what? Easily we can find this p and q, prime numbers p and q, whose product is n. So what does it mean? What is that we are going to gain or lose with that? Now, many of you, those who are from computer science background, even other people also, you must be knowing that. Now, for encryption, this RSA crypto system is used. Okay, no? RSA algorithm is used. We say that whatever encryption, for example, online banking and all, no, encryption method which is based on RSA, we say that it is secure. Why it is secure is, people say that is, there we are given integer n. In order to find the key, we need to find two prime numbers p and q such that n equals to p and q. Classical computers, they are not able to find this in less time. They take crores of years. Okay, but if we quantum computers, if they with the sufficient number of qubits, if they become reality, this easily p and q can be found. In that case, what happens? This encryption system is not going to be secure anymore. That is the problem. Is the point clear? See. Encryption which is based on RSA algorithm is secure. Why? Because the classical algorithms, okay, no, using classical computers, given n, it is impossible to find p and q in reasonable time, where p and q are prime numbers and whose product is n. Okay, it is not possible in reasonable time, but quantum computers can easily find this p and q. Quantum computers can easily find this p and q by using what is the algorithm for the integer factorization, that is called Schwarz algorithm. This is the breakthrough result. Okay, that means all encryption methods which are based on RSA, they are not at all secure. People will be able to easily find out our passwords. Okay, that's why people started developing new research area called post-quantum cryptography. Okay, if quantum computers available, if people are able to solve this problem, still that should be secure. What to do for that? That area is called post-quantum cryptography. Okay, now have you understood at least one problem where classical computers are not able to solve? Quantum computers are able to solve it. With that, what is the problem we are going to face? Is that clear?
Yes, sir.
Okay. Now, is it clear why quantum computing is required? That means there are some difficult problems which classical computers are not at all able to solve in reasonable time. But these computers, they have shown that they can solve it in reasonable amount of time. Is that okay? Is why quantum computing clear? Next. So some of you might have heard the word quantum supremacy. Okay, no? So it shows that, okay, these quantum computers, they can do something beyond the capabilities of classical computers. Okay, no, beyond the capabilities of, or they are going to be superior than any classical computer, fastest supercomputer in the world also you take. At least for one problem. At least for one problem. Now, what are the quantum processors which demonstrated quantum supremacy? In October 2019, Google's Sycamore quantum processor, QPU, they showed that a problem which takes 10,000 years to solve it on classical computers, fastest supercomputers, it takes only 200 seconds. That means whether supremacy is achieved? Yes. Okay. Similarly, in December 2024, Google's Willow processor, quantum processor, they solved a problem which takes, this is 10 power 25, sorry, which takes 10 power 25 years on supercomputers. Here it solves it in only 5 minutes. Where is 10 power 25 years? That is after 126 zeros, which takes that much time, that many years of time. But this quantum computer, it solves it in only 5 minutes. It is an example. No, similarly, very recently, Mazarano processor that you might have seen, some of you might have seen. Okay, now Microsoft announced this, and they claimed that it is going to change this and do computation more efficiently. Okay, and you might be aware that in Amaravati, so from AP, Andhra Pradesh, so from January 1st to 2026 onwards, they are going, there they are going to have a quantum computer with how many qubits?
128 qubits, I think.
100 plus exactly 150 or 156
150 qubits, sir.
150 something exactly. I don't remember. Okay, that is going to be big thing. No, now at least now we are in infant stage of this quantum computing. Okay, so now at least what are the applications? As usually, any area, any domain, whether it is ML or DL or AI. So these are the usually areas where people talk about, whether it is applicable or not. Similarly, as expected, this quantum computing with the combination of AI and ML, it is going to revolutionize research in these things. Okay, already cryptography I have mentioned explicitly. Similarly, other domains. Okay. Next question is, so far we have seen what is quantum computing, why quantum computing. Next, who are the people who contributed most to this domain? So Richard Feynman introduced the idea of quantum computer in 1981. Next, David Deutsch, with some simple problem, he was able to show that these quantum computers can solve this problem very much efficiently than these classical computers. One simple problem. This is only demonstration type of example to show that quantum computers are more powerful than classical computers. This is the first algorithm. It is known as Deutsch algorithm. Deutsch algorithm. Next, this is the actual result by sorts. What for the sorts algorithm is used? Just now I have mentioned, to solve integer factorization problem. Okay, now factorization problem. Okay, using this, what happens? The problem which is not possible to solve in polynomial, it has become polynomial time solvable in quantum case. This is the best example. Okay, no, very well-known algorithm, more powerful algorithm with the practical applications. That's what RSA I mentioned. No? Okay. Next one is Grover's algorithm. So all of us know that if we are given n elements, if you want to search for one element in this n elements. How much time we require? In the worst case, we are given n elements. Out of that, one element we need to find. How much time we require? Out of
n minus 1 times.
N minus 1 or n times also, sir. Because last element may not be equal to that element. No, it may not be present also.
Okay. Then n times.
N queries, n comparisons we need to perform. N queries we require. But
Sir, it needs n times.
Love Kumar Grover. This is in the worst case, sir. In the worst scenario, we require n queries. But Love Grover, he has shown that it is possible. It is asymptotically order of n time. He has shown that we can do this in order of root n time. Root n square is n no. That means quadratic improvement. This is again one breakthrough result. Okay, now whoever talks about quantum computing, they talk about these two algorithms mainly, computation point of view, Shor's algorithm and Grover's algorithm. Okay. Anyhow, these two are there as part of your schedule. Okay, no, FDP. And the most celebrated book is Quantum Computation and Quantum Information by Nielsen and Chang. This PDF is available. You may download it. It is available for free online. Okay, this is considered as Bible of this quantum computing. Okay. So far we have only talked about what? We have only talked about what is quantum computing, why quantum computing. Whether 2 points are clear?
Yes, sir.
Only 2 things. What is quantum computing? And why quantum computing?
Clear, sir, clear.
Okay, thank you, sir. So next we will try to understand some fundamentals of this quantum computing. Okay. All of us know what is a complex number, no? It is of the form a plus ib. But what is I square? I square is -1. So these are all complex numbers, a plus ib form. Every real number is a complex number or not? With imaginary part being 0. Correct, no? Is 8 a complex number?
8 plus j.
It is a real number. Is 8 real number? Yes. Is it a complex number? Yes. With the imaginary part being 0. Is that correct?
Yes, sir.
Complex numbers is superset of real numbers. Okay. Okay. Now, how do you represent complex numbers? A complex number in 2D plane. So, for example, we have a plus ib. A plus ib. How do we represent? One side you take real part, one side you take imaginary part. Real part a units on real part. This is origin. B units on imaginary part. Now this is the point. Now what is the distance from origin to that point? What is the distance from origin to that point? Now it becomes right angle triangle. A units here. How many units here? B. Now we can apply Pythagoras theorem. What is that we get? This is square root of a square plus b square.
A square plus
so
b
this
square.
is the magnitude or length of this complex number. Is that okay? Is that okay? Square root of a square plus b square. Next. Now, all of us must be knowing what is a row matrix. What is a row matrix? Matrix means it contains some rows and columns. No? If it contains only one row, matrix with only one row, that is called row matrix. It can have either one column or more than one column, it doesn't matter. Is it a row matrix? 257. 257.
Yes, sir. Yes, sir. Yes, sir.
What about this? Is it a row matrix?
Yes, sir. Yes, sir.
This is also a row matrix. Is it a row matrix? Yes, this is also a row matrix. Now, similarly, what we can talk about column matrix, which contains only one column. So this is an example for column matrix. Is that okay? Similarly, is it an example for column matrix or not? Yes.
Yes, sir.
This is also an example for only one row, one column. That is also okay. One column is there, no, sir? Okay. Now let us say I am talking about a system like a coin system. Let us say X is a coin system. What are the outcomes of this system? Either it is going to be heads or tails, no? Heads or tails. Is that okay? Okay. Now I'll fix the order like this: heads first and tails next. So these are coin system. These are the outcomes possible. Heads is one possibility. Tails is another possibility. First I consider heads. Next I consider tails. Now I have seen that I have this coin after rotating, after tossing a coin, I saw that I got heads. I got heads. Now heads, I can heads place I put 1. Tails place I can put 0, like this. You can even consider it as probability of getting heads, the probability of getting tails. That means already I got heads. That's why I put 1 in heads position, tails position 0. Now if it is tails in the similar style, how do we write?
0, 1.
0, 1. This is head spot. This is tail spot. Okay. And this notation, we can also write it like this is ket heads, ket of heads. This is ket, similarly ket of tails. Is that okay? Is that okay? So first you fix the order like this: heads first and tails next. Then you write matrices, column vectors like this. Then first one I call it as ket heads. Second one I call it as ket tails. Similarly, if my system is, I am talking about 0, 1 system. My outcome is either 0 or 1. Now I have got outcome as 0. Then what is the matrix corresponding to that? Order is 0, 1. It is 1, 0. If I get outcome as 1, what is the matrix corresponding to that? By fixing, is this okay? See, are you getting this? Is this clear? What is head styles? How did I write 0, 1, 1, 0? Is that clear?
Yes, sir.
Yes, sir. Yes, sir. So now similarly, similar to this notation, how do we write this 1, 0? Ket 1. Sorry, ket 0. This is ket 1. Is that okay? Okay. Even if it is not clear also, okay, after some examples, it will be more clear to you. Let us say this. This ket notation as well as bra notation, these are simple or convenient ways to represent matrices. Okay, now matrices. Now 1, 0, as I mentioned earlier, it is ket 0. Is it clear why this is 0, 1? I have seen that and I got 1. That's why I put 1 here and it is 0. I here outcome is 1. That's why I have put 1 in the second position and first position 0. Is this okay? These are column vectors. Ket means column vector. This we read it as ket 0. Ket 0. Okay. This is ket 1. This is ket 1. This you should not forget. We use it. Okay. We use it. Now what is bra 0? What is bra 0? Bra 0 is conjugate transpose of
Ket 0.
Ket 0. What is ket 0? Ket 0 is 1, 0. What is transpose of this 1, 0? What is transpose of 1, 0?
0, 1.
No. 1, 0 only. This is column matrix. This is row matrix. Sir.
Row matrix.
Okay, na sir. This is column matrix. This is transpose. What is conjugate? What is conjugate of A plus IB? Conjugate of A plus IB is A minus IB. What is conjugate of 2 plus I3? It is 2 minus I3. What is conjugate of 2? What is conjugate of 2?
2 only.
Minus 2.
2 only. Because if it is the imaginary part, it becomes negative. There is no imaginary part here, same thing. Now, what is, you take conjugate of 1. Conjugate of 1 is 1 only. Conjugate of 0 is 0 only. Finally, we got 1, 0. This is called bra 0. Is that okay? What is bra 0? How we got 1, 0? Is that clear? Similarly, what is bra 1? Transpose of this you take. Transpose is 0, 1. Conjugate each element. All are real numbers. Conjugate, if you do also, same thing we get. Same thing we get. Is that okay? Is that yes, sir.
Yes, sir.
Yes, sir. Okay, so ket 0, ket 1, no one should forget. Okay, ket 0, 1, 0, ket 1, 0, 1. Okay. Now we can multiply this. What is ket 0, bra 0? Ket 0 is 1, 0. What is bra 0? 1, 0. This is normal matrix multiplication. If we do it, we will get 1, 0, 0, 0. Okay. Normal, this is normal matrix multiplication. Okay, this you can do 1 into 1, 1. Okay. Similarly, what is ket 0, bra 1? Ket 0, you write what is the value, matrix form. This is direct notation, this is matrix form. Bra 1, what is the value? 0, 1. Again multiply, you get this. Is that okay? Similarly, what is ket 1, 0? Now, if you observe here, this is 0, 0 position. This is 0, 1. This is 1, 0. This is 1, 1. Here 0, 1 means 0, 1 position, 1 remaining all 0. 1, 0 means 1, 0 position, 1 remaining all 0. Similarly, what is ket 1, bra 1? Ket 1, bra 1, can you guess? Last position, 1 remaining all zeros. This notation given by Dirac, and this is known as Dirac notation. Okay. Now, only this thing, if you remember, that is enough. Other things automatically. Ket 0 is 1, 0. Ket 1 is 0, 1. This is Dirac notation. This is matrix form. Is that okay? Are any confusion here?
Clear, sir. Clear.
Okay.
Clear.
Okay. Okay. Now you take Thank you. Now, quantum information system. So any system we have input, and we will finally get output. Okay. So this input has to be transferred to output. For that, we perform different operations. That means here our algorithm works. Algorithm means we perform different operations. No. Okay. Different operations. Now let us say time is from left to right. At time t0, my quantum system is in state S0. Okay. Now I performed some operation here. Let us say time is t1. I performed some operation. My quantum state may change to S1. Next, I perform one more operation here. T2, some operation, my state may change to S2. Keep on doing like this. Here, last operation I am performing. Tn, state may change to Sn. Is that okay? Now, finally, we will get some state here. Okay. Whatever state here, again, this is quantum state. But if you want to really see the output, we need to go for measurement. That I will discuss next. Okay. Then output is going to be always classical, like 0, 1, 0, 1. This is the way how quantum information system works. Okay. Now we should know how to give this quantum state as input to quantum system. What is quantum state? Okay. That we will discuss. Now this quantum state is simply represented by column vector. Now you know what is a column vector or column matrix. What is column vector? It contains only one column. Is 1, 0 a column vector? Is 1, 0 a column vector?
Yes, sir. Yes, sir.
Yes. Okay. is 20, 30, 40. Is it a column vector? Yes. Yes.
Yes, sir.
But whatever we write like this, all things we cannot call it as quantum states. They should satisfy some two properties. Two properties. Okay, they should satisfy two properties. So what are they? What are they? One is all entries in this column vector, they are complex numbers. Means every real number is also complex number, so no problem. The other one is every entry you take here, one. So in this example, for example, I'm talking about this. Each entry you take, one is the entry here. You take modulus of that, mod 1 square, plus second entry is 0, mod 0 square. This entire value should be 1. This is the second condition. All entries are complex numbers. What is the next condition it has to satisfy? What is the next condition? Sum of the absolute valued squares of the all entries in the column vector must be 1. Must be 1. Now you tell me whether this column vector satisfies that condition. 20, 30, 40, whether it satisfies that condition?
No, sir.
No. Whether it satisfies this condition?
Yes.
Yes. 1 by root 2, 1 by root 2. Whether it satisfies the condition? Yes, sir.
Yes, sir. Yes, sir.
Even if I put minus 1 by root 2?
Again, yes, sir. Yes. Yes, sir. Yes, sir. Correct.
What about this? This also doesn't satisfy. That only we call it as quantum state. That's all. And simple terms, that entire thing we call it as Euclidean norm is 1. You can read this second part. First one is all are complex entries. The other one is Euclidean norm is 1. Okay. Sum of the absolute valued squared of the entries must be 1. Okay, we will see with examples. Now, if you are given a column vector like this, how do you know that? What is the norm of this vector? It is pronounced as norm V. Okay, no, it is denoted as mod alpha 1 square plus mod alpha 2 square plus and spawn mod alpha n square. But when we say Euclid now, we take square root. Okay, here mod is there. Okay. This is the Euclidean norm. Is it okay? Okay, anyhow, we'll see more examples now. Okay. Now, what is a qubit? Qubit stands for quantum bit. Okay, now qubit means it is quantum bit. Like how we have bit in classical computing. Bit is the basic unit of information, no? In classical computing. Here, qubit is the basic unit of information in quantum computing. Okay, no? In quantum. Classical information, bit is the basic unit. Quantum information, qubit or quantum bit is the basic unit. Okay, basic unit. Okay, but whenever we say qubit, that means we are talking about quantum state where this vector contains only 2 entries. Whenever I say qubit means this vector should qubit means it is also a quantum state. Only specialty is this quantum state contains how many entries? How many entries? How many entries? Column vector should contain how many entries? Only 2 entries. One is for 0, the other one is for 1. That's all. It is a quantum information system with only two outcomes. One is 0, one is 1. That type of quantum state we call it as qubit. Is that okay? Is that okay? Qubit means qubit means it is also a quantum state. It is also a quantum state. But what is the condition it has to satisfy? There should be only 2 possible outcomes. That the column vector should contain only 2 entries. Only 2 entries. Is that okay? Okay, we will see with example. Now 1, 0. Is it a qubit or not? Is it a qubit or not? Yes. First of all, is it a quantum state?
Yes.
Yes. It can,
Satisfies both conditions.
we have already seen. It is a quantum state. Mod 1 square plus mod 0 square is 1. It is a quantum state and it contains 2 entries. Hence, it is a qubit. What is the other form of writing 1, 0? Ket 0. Both are same. No, whether I write 1, 0 or ket 0, both mean the same. Okay. You don't worry about this right now. Okay. Now, what about 0, 1? Is it a qubit?
Yes, sir. Yes, sir.
So, mod 0 square plus mod 1 square. Is it 1? Mod 0 square plus mod 1 square. Is it 1?
Yes, sir. Yes.
It contains only 2 entries and this condition is also satisfied. Hence, it is a qubit. What about this? Is it a qubit?
Yes.
Mod 1 by root 2 square plus mod minus 1 by root 2 square. Is it 1 or not? Is it 1 or not?
Yes, sir. Yes, sir. Yes, sir.
Is it 1 or not?
Yes, sir. Yes, sir. Sir, it is one, sir.
1 by root 2 mod 1 by root 2 square plus mod minus 1 by root 2 square. It is 1 by 2 plus 1 by 2, which is equals to 1. That means it is correct only, no? Is that okay? This is norm. Euclidean norm is 1. Okay, other way Euclidean norm is 1. What about this? What is 2 plus 2i by 3? This can be written as 2 by 3 plus 2 by 3i. Is that okay? 2 by 3 plus 2 by 3i. What is the condition it has to satisfy? Mod 2 plus 2i by 3 square plus mod 1 by 3 square equals to 1. What is 2 plus 2i by 3 square? Okay. So mod a plus bi square. What is this value? What is this value? What is mod a plus bi? We have already calculated. No.
Root of
What is this value?
root of
Square root of a mod a square plus mod b square.
Mod A square plus mod B square.
What is this square? This square means this square and this square gets cancelled. We will get mod a square plus mod b square. Is that okay? Mod a square plus mod b square. Now you tell me what is a here? A is 2 by 3. What is b? B is also 2 by 3. So what is this value? 2 by mod 2 by 3 square plus mod a square plus mod b square plus 1 by 3 square means 1 by 9. This is 4 by 9 plus 4 by 9 plus 1 by 9. Is it equals to 1 or not? Yes. So now, because these are really complex numbers with imaginary part non-negative. Others are complex numbers, but imaginary part negative, 0. Imaginary part non-zero here. Okay. Is it a quantum state? Is it a quantum state? Valid quantum state?
Yes, sir.
Is it a qubit? Is it a qubit?
Sir. Yes, sir. Yes, sir.
Yes, only 2 entries. No, it is a qubit. What about 1 plus 2i by 3, 1 by 3? Can you do it and tell me? 1 plus 2i by 3. This we can write it as 1 by 3 plus 2 by 3i. What is this square? It is 1 by 3 square. Mod 1 by 3 square plus mod 2 by 3 square. It is 1 by 9 plus 4 by 9. This is 5 by 9. This side 5 by 9. This is 1 by 9. Total it is 6 by 9. Is it equals to 1? No, sir. Is it a valid quantum state? Is it a valid quantum state?
Valid quantum state. But
No. It is not a valid quantum state. No, sir.
2 states, no, sir.
1 plus 2i by 3, 1 by 3.
Only 2 bits are there, sir. But
correct.
Euclidean norm is not satisfied.
Because first it is a quantum state, but only with the 2 entries, that is called qubit.
Yes, sir.
2 entries, okay, but first of all, it is not a quantum state at all, no.
Yeah. Okay, sir.
To be qubit, first it should be quantum state, no, sir.
Yes, sir.
Simply 2 entries, we cannot call it as qubit, okay? Quantum state with the 2 entries here, okay? Is that okay, sir? Okay.
Yes, sir. Okay, sir.
Okay. Now, see, all of us know that ket 0 is how, what? 1, 0. Ket 1 is 0, 1. Is that okay? Is that okay? Now, how to write 1, 0? 1, 0, can we write it as 1 into 1, 0 plus 0 into 0, 1? Is this correct? What is 1 into 1, 0? 1, 0. 1 into 1, 1. 1 into 0, 0. Plus 0 into 0, 1?
0,
0, 0. Overall, it is 1, 0 only, no?
Easy.
Is this correct? Now, what is 1, 0? 1, 0 means ket 0. What is 0, 1? It is ket 1. Is that okay? Same ket 0, I can write it combination of both ket 0 and ket 1 like this. Or we can assume that it is alpha ket 0 plus beta ket 1 form, where alpha is how much? Alpha is how much? Alpha is how much?
Alpha equal to 1, beta equal to 0.
Equal to 0. Okay.
0. Alpha is 1, beta is 1, beta is
How to write 0, 1? 0, 1, can we write it as 0 into 1, 0 plus 1 into 0, 1? All of you agree with this? Is this okay? Zero into 1, 0 is 0, 0. 1 into 0, 1 is 0, 1. If I add these two, 0 plus 0, 0, 0 plus 1, 1, 0, 1. Is that okay? Now 1, 0, I can write, instead of writing 1, 0, I can write it as ket 0. That's why here 0 times ket 0. 0, 1 is ket 1. 1 times ket 1. Is that okay? Is that okay?
Yes, sir.
Okay. Now, why did I write this other form? It is also alpha ket 0 plus ket 1 form. It is also alpha ket 0 plus ket 1.
Sir, your voice is strange, sir.
Okay. Maybe I think coordinators, they might have unmuted, and that could be the reason. I think now it's not echoing, no?
Now it is clear, sir.
Okay,
It is clear, sir. It is clear.
Give me 1 minute, sir. Actually, we both want it is an interaction section, and it is going to be like that only, because the way you are asking questions and people are responding. The only problem is everybody is speaking at the same time. That's the only problem. I can unmute all of them. I can mute all of them also. But if I mute it, there is no use. So that's why I request participants to switch on when you are asking the question. Again, switch off. Thank you. Thank you very much. Sir, please continue, sir.
Thank you, sir. Thank you for clarification. Now, what about 1 by root 2 minus 1 by root 2? We know that it is a qubit. Can we write it something like this? 1 by root 2 minus 1 by root 2. Can we write it as 1 by root 2, 0 plus minus 1 by 0 minus 1 by root 2? Is this correct? 1 by root 2, 0 plus 0 minus 1 by root 2. Is this okay?
Yes, sir.
Yes. Okay. Thank you. Now, first matrix, column matrix, I'll take 1 by root 2 outside. 1 by root 2, 1, 0. Second column matrix, I'll take minus 1 by root 2 outside. Then it will be 0, 1. 1 by root 2. What is 1, 0? 1, 0, we know that ket 0. What is 0, 1? Ket 1. 1. Again, I have written combination of ket 0 and ket 1. No, this matrix also. This is the one we got. Is that correct? It is again alpha ket 0 plus beta ket 1 form, where alpha is 1 by root 2, beta is minus 1 by root 2. Is that okay? Now, if I write qubit in this form, alpha ket 0 plus beta ket 1 form, what is the condition it has to satisfy? What is the condition it has to satisfy? This is mod of this square plus mod of this square is equals to how much? 1. 1. That means first 1 by root 2 is nothing but our alpha, no? Second minus 1 by root 2 is nothing but our beta, no, sir? Okay. First 1 by root 2 is our alpha. Second minus 1 by root 2 is our beta. That means what is the condition it has to satisfy? Mod alpha square plus mod beta square is, this is our alpha. This is same 1 by root 2. This 1 by root 2 only it has come here. This minus 1 by root 2 only has come here. Okay. So alpha ket 0 plus beta ket 1 if I take, what is, simply if I write this state as like this, what is the condition it has to satisfy? Without giving further details, mod alpha square plus mod beta square equals to 1, no? This condition has to be satisfied, no? Is that okay? Yes, sir. Now I can define qubit instead of matrix form like this. I can define qubit like this also, no? Alpha ket 0 plus beta ket 1, where mod alpha square plus mod beta square is 1. Now, this is a column matrix. Here all are complex numbers. So alpha is a complex number, beta is a complex number. This is more formal way of defining qubit. Okay. Now we define qubit like this. Now we are familiar with the notation. This is ket psi. This is general form of defining qubit. More formal definition of qubit. Alpha ket 0 plus beta ket 1. Now we know that ket 0 is 1, 0. Ket 1 is 0, 1. Okay. Now it is nothing but linear combination of ket 0 and ket 1. No. 0 state and 1 state. Two possible states. Okay. No? Two possible states. This is 0, ket 0 and ket 1. And this alpha beta are complex numbers. Alpha beta are complex numbers. They are called probability amplitudes. What is the condition if they have to satisfy, as we discussed earlier? Mod alpha square plus mod beta square is how much? Mod alpha square plus mod beta square is how much?
Should be 1.
1. 1. Now is it clear, sir? So whenever we say qubit, we can simply say alpha ket 0 plus beta ket 1. Okay? Where alpha beta are what? Complex numbers. They are also called probability amplitudes. Other name for that. Okay? What is the condition it has to satisfy? Mod alpha square plus mod beta square is 1. Now it is only linear combination of 0 and 1. No, that is the only thing. Qubit means it is linear combination of both 0 state and 1 state. Some part is in 0 state, some part is in 1 state. Total if we take, it should be 1. Is that okay? Is that okay? Are any doubt here? Okay, we will see with example again. Now you tell me, is it a qubit or not? Ket 0, is it a qubit or not? Is it a qubit or not?
So it represents 1, 0, which means sum is 1 and there are 2 elements.
Yes, sir. Now can we use this notation, sir? That notation anyhow we have learned. Now can we use this notation? Ket 0. How to write it in this form? Alpha. Alpha if I take 1 times ket 0 plus 0 times ket 1. Can you write, sir? Ket 0 is it same as this?
Yes, sir. Yes, sir. We can write.
Here it is alpha. Here, linear combination of ket 0 and ket 1. What is the condition? Is it satisfying? Mod alpha square plus mod beta square. Is it 1? Yes. Hence we say that it is a qubit. Over. Ket 0, is it a qubit or not?
Yes, sir, it is qubit.
Similarly, try to is ket 1 qubit or not?
Yes.
Yes, qubit.
Here, what is alpha value?
0. Alpha value is 0 and beta value is 1.
Beta is 1. So here alpha is 0, beta is 1. It is satisfying that. What about here? What is alpha value, beta value? Is it a qubit or not?
Yes, sir.
What is
Alpha is
alpha
1 by
value?
root 2. Alpha beta 1 by root 2.
Yes,
1
sir.
by root 2.
Thank you, sir. What about this? Is it a qubit or not?
Yes, sir, qubit.
Okay. Okay. What about this fifth one?
It is also
Yes.
qubit, sir.
Yes, sir. This is also qubit. We have already seen 2 plus 2i by 3, 1 by 3. This is 2 plus 2i by 3 mod this square plus 1 by 3 square. This value is 1, no? We have already calculated this. Is that okay? What about this? Is it a qubit or not?
No, sir.
No.
No, sir. It is
Why?
not
Because
qubit,
this
sir.
becomes 6 by 9, not 1. Okay? This is no. No is correct answer here. What about this?
No, sir.
It is also not a qubit, sir. It is not a qubit, sir.
What about this?
Yes.
Ket 0 plus ket 1. Nothing is there means 1 times ket 0 plus 1 time ket 1. No, that is the meaning. No,
It is not a qubit, sir.
thank you very much. Thank you very much, sir.
Not a qubit, sir. No.
No. No is correct answer. Why? Because mod alpha square plus mod beta square, if I take, it is 1 square plus 1 square root 2 will get, no, not 1. Okay. This is not a qubit. Red color, they are not qubit state. What about 0 minus 1? Ket 0 minus ket 1?
No, sir. Not a qubit.
Same
No,
reason.
sir.
Same reason here. Okay. Now this linear combination only. Alpha ket 0 plus beta ket 1. No, combination of 0 state and 1 state. This linear combination only, that means what does it mean? Existing in both 0 state and 1 state at the same time. That only we call it as superposition. That's all. That is more formal way of defining. See, here this qubit exists in 0 state as well as 1 state. No, this is some part in 0 state, some part in 1 state, some part in 0 state, some part in 1 state. This linear combination only we call it as superposition. Is the definition of is superposition clear? We are aware of what is linear. Linear combination? No. Here it is linear combination of ket 0 and ket 1. That's all. With the additional constraint. What is the condition? Mod alpha square plus mod beta square is 1. Superposition means existing in multiple states at the same time. 0 here, 2 qubit means 2 possible states. 0 state also it is there, 1 state also it is there. Okay, now at the same time. Okay. Is the definition of qubit clear? Okay. You tell me, is it a qubit or not? Third one. We know that we have already seen this two. Third one, is it a qubit or not?
Qubit.
Yes, sir.
I by
Yes,
root
sir.
2. I by root 2.
It is also qubit, sir.
Qubit, sir. I by root 2 is same as
Magnitude same.
0 plus 1 by root 2 into I. Mod 0 square plus 1 by root 2 square, which is nothing but 1 by 2. Okay. So this is a qubit. What about this? Is it a qubit or not?
Qubit.
Yes, sir.
Yes. What about
Yes,
this?
it is a qubit.
Qubit.
Yes, sir.
Yes, sir.
What about sixth one?
No, sir. No, sir.
It is not a qubit, sir.
No.
It is not a
Not a qubit.
qubit. What about this one?
Not a qubit.
Okay. Now we talked about the two states now. Okay, now quantum state where only two outcomes means that we call it as a qubit. Now let us talk about a system where I have four possible outcomes. If I talk about ceiling fan, it may be in high state, medium state, low state, or off state. Okay, this is the ordering I am following. Now I have observed that my ceiling fan is in high state. Then what is the corresponding column vector? We have seen that it is in high state.
1000.
Means I place remaining all zeros. Is that okay? Yes, sir. This we call it as ket high notation. Now, can you define what is ket medium?
0100.
That's all, sir. What is ket low?
0010.
Now, is it a valid quantum state? 0010.
Yes, sir.
Yes, sir.
Mod 0 square. Okay. Now, is it a valid quantum state?
Yes, sir.
Yes. We can write it as a linear combination of all these four states or not. Is it possible or not?
Yes, sir. We can write.
Sir, can you give answer, sir? Can we write it like this? 1 by root 2, 0, 0, 0 plus 0, 1 by root 4, 0, 1 by root 4 plus 0, 0, 0, 0 plus 0, 0, 0, 1 by root 4. Okay, this is 0. Now I can take 1 by root 2 common, then it will be 1 triple 0. Here if I take second one, 1 by root 4 common, 0, 1, 0, 0. If I take 0 common, can we write something like this? If I take 1 by root 4 common, can we write something like this? Is that okay? Now what is 1 triple 0? This is nothing but ket high.
Kent high.
1 by root 2 times ket high. This is 1 by root 4 times
Kent medium.
Now is it clear? How did we get this? Is that clear? Yes, sir.
But some of the qubits are not one.
Correct. 1 no, madam. Mod 1 by root 2 square is 1 by 2 no, madam. Mod 1 by root 4 square is 1 by 4. 0 square is 0. 1 by root 4 square is 1 by 4. 2 1 by 4 is half. Half plus half is 1 no.
Got it, sir.
Okay. Thank you. Is this okay? Okay. Now, for example, say NIT Warangal, they allow MTech CSC, they want BTech as BTech CSC, BTech CSIT, or BTech AIDS. These are the possible states. Now, quantum state of second MTech CSC, it is represented like this. Is it a valid quantum state?
Yes, sir.
Yes. How to write it in terms of this allowed outcomes?
One by root 2.
By root 2 zeros.
BTech CSC.
Yes, sir.
1 by root 2 BTech CSIT.
Yes, sir.
plus 0 into beta KADS.
Is this correct?
Yes,
Same
sir.
procedure if you follow, we can come up with this. Okay. Okay. Next question is, so I talked about coin. We toss a coin. Once it falls on ground, without any confusion, we know whether it is in head state or tail state. Okay. This is called measuring. This is called measuring. Once it falls on ground, we see with our eyes, and without any ambiguity, we say that our coin is in one out of the two allowed states. Is that correct? Similarly, if I roll a die, there are 6 spaces. If I roll a die, okay, then once it stops, we'll see top only one number, let us say 4. Then we say that, okay, it is in state 4. So, measuring means once this coin example, if you understand, in coin example, once coin stops and falls on ground, what we see with our eyes, what is the state it is in, whether head state or tail state, without any ambiguity, we say one of the possible state as answer. Similarly, die also like this. Okay. So that ambiguity will not be there. With clarity, we say which state the system is in. Okay. When the system is in probabilistic state, if you measure, probability will go. With the clarity, we know what is the outcome. Now, I am talking about a system where 2 states are allowed, 0 or 1. 0, 1. If I go for measurement, what are the outcomes I see? If I talk about coin system, there are heads and tails. What are the outcomes we get when we go for measurement? What are the possible outcomes?
Either head or tail.
That
0 or
one
1.
One out of these 2, no, sir.
Yes.
Now here also, if X is a bit system, when I go for measurement, what are the possibilities? We get either 0 or 1. Which one we don't know. Is that okay? In this
Yes,
case, what is the outcome?
Yes, sir.
0 heads or tails, but which one we don't know. In this case, high, medium, low or off, but which one that we don't know. In this case, 1 to 6, which one again we don't know. Is that okay?
Yes, sir.
Now, okay. Now see, our system, again coin system, allowed states are heads or tails. Now I have seen that my coin system, it stopped and I saw heads. Then what is the state it is in? After measuring, I observed that heads is on top. We got heads. Then what is the state?
0, 0, 1.
No, 1, 0, sir. Ordering is
1,
this.
0. Yes.
1, 0.
Ordering change.
If I get tails, what is our order?
0, 1.
0, 1.
0,
So
1.
this we can also write it as get heads, no? This we can write it as get tails.
Yes.
Is that okay? Similarly, is this okay? Now in this case, if I get 0, what is the column vector corresponding to that?
1, 0.
1, 0. Thank you, sir. Or simply we can call it as ket 0, no, sir?
Ket 0.
Ket 0 or 1, 0. Okay. If we get 1,
0, 1.
0, 1.
0, 1 or ket
1
1.
or cat 1.
Ket 1.
Okay, okay, thank you. Now we got 1. We are talking about die, 6-sided die, and after observing, we saw that we got 1. Then it is represented by column vector. What? This is the ordering. 1, 2, 4, 1, 2, 3, 4, 5, 6 is the ordering. It is represented by how? What?
5 zeros, 1, sir. Last.
No, see, we got 1. 1 is here only, no, sir. 1 plus 1, remaining is 5 zeros. Ket 1.
Yes, sir. What is the matrix?
1 5 zeros.
1 5 zeros. If I get 2, what is the matrix?
0 1 4 zeros. Ket 2.
Ket 2. Similarly, 3.
Same, sir.
001 000.
4. Is it clear now how we are getting?
Yes, sir.
Okay. Yes, sir. Okay. Now, if you are given column vector with 2 entries like this, any column vector with 2 entries like this, for example, this is one example, n 1 by 5, 4 by 5. Is it possible to write it as a linear combination of these 2 vectors?
Yes, sir.
How, sir?
1 by 5 into 1 0 plus 4 by 5 into 0 1.
4 by 5 into 0 1. Thank you, sir. Same thing I can write in a direct notation like this, no, sir?
Yes, sir.
1 0 is get 0, 0 1 is get 1.
Ket 1 plus 1 by 5 ket 0.
Okay. So not only 1 by 5, 4 by 5, in general, any AB is given, column matrix with 2 entries. We can write it as a linear combination of these 2 vectors. Hence, we say that if these 2 vectors are there, we can easily play with this 2-dimensional space, entire space. Any 2-dimensional vector, column vector with 2 entries, we can represent using only these 2 entries, only these 2 matrices. Then I don't need other matrices to represent anything in 2-dimensional space. No, I can play with only 1 0 and 0 1. Is that okay? If I want to represent 1 by 5, 4 by 5, I will represent it this way. I need not explicitly say 1 by 5, 4 by 5. No. Is that okay? Are you getting the point? No. Any column vector with the 2 entries, we can write it as a linear combination of 1 0 and 0 1. Hence, we say that this is a basis for Similarly, 1 by 2, 1 by 2, 1 by 2. How to write it?
1 by 2 ket 0 plus 1 by 2 ket 1.
Ket 1. That's all. Can you tell me anything which is not possible to represent using these 2 entries? 2 dimensions. Nothing. Whatever you take, automatically first one becomes coefficient of ket 0, second one becomes coefficient of ket 1. That's all, no? That's why this is called basis, and this is also called standard basis or computational basis. Okay, standard basis. These vectors are called standard basis vectors. Now, similarly, 6 dimensions, if you want to give basis vectors, like this you can give, no? Is this okay? 6 entries, 6 column vectors. If I want to represent this, how do we represent? 1 by 6 into this, plus 1 by 12 into this, 1 by 12 into this, 1 by 3 into this, 1 by 6 into this, 1 by 6 into this. Why? Because that respective position 1 is there. Take summation. Is that okay? Is that okay? So this is basis for 6-dimensional space. Can you give basis for 4-dimensional space? Basis for 4-dimensional space? Hello?
1 000 0 1 0 0 0 0 1 0
Yes,
0 0 1.
Yes.
0 0 1. Okay. Okay. Now this one, if you represent ket 1, similarly we can do this. Okay. Now, if you measure a quantum state, what happens? Without any ambiguity, one of the possible classical states we get as outcome. No? If you measure a quantum state, one of the plausible classical states we get as outcome. No? Now, if I measure this quantum state, what is that we get? What are the outcomes? Either we get 0 or we get
11.
if I measure this quantum state, there are only two possibilities, no, 0 state and 1 state. So I may get 0 state or I may get 1, no?
Yes.
Now, what is the probability of getting 0? It is given by its amplitude square. Mod 1 by root 2 square. 1 by 2. Probability of getting 0 is 1 by 2. What is the probability of getting 1? This is also mod 1 by root 2 square. It is also 1 by 2. Total probability is 1. Is that okay? In this case, what is the probability of getting 0?
Again, 1 by 2.
What is the probability of getting 1, sir?
1 by 2 only, sir.
1 by 2 only. Total probability is 1. In this case, what is the probability of getting 0? What is the probability?
8 by 9.
8 by 9. Thank you very much, madam. What is the probability of getting 1?
1 by 9.
Total probability is again 1 now. In general, alpha ket 0 plus beta ket 1. What is the probability of getting 0? Mod alpha square. What is the probability of getting 1? Mod beta square. That's all. Okay, this is alternative way of defining this. Once you are familiar with this ket notations, bra notations, you can textbooks, no, you might find something like this also. Okay. So what is the probability of getting 0 here?
8 by 9.
Whether it is 2 plus 2i or 2 minus 2i, it doesn't matter. In both cases, you will get 8 by 9. What is the probability of getting 1?
1 by 9.
1 by 9. Ket 0. Ket 0, we can write it as 1 into ket 0 plus 0 into ket 1. What is the probability of getting 0?
1.
1.
1. What is the probability of getting 1?
0.
0. In this case, sir?
0, 1, sir.
Now, in this case, what is the probability of getting 2?
1 by 9.
1 by 9. Probability of getting 4?
1 by 9.
1 by 9. If you calculate probabilities for all and the add, then it should be 1. So far, what is that we have discussed? What is quantum computing? Okay. Why quantum computing? Okay. Who are the people who contributed most to the quantum computing? Next one is, what is qubit? What does measurement mean? Only these things we discuss. No? In the process, we also talked about superposition. Up to this, is there any doubt, sir?
No, sir. Everything is clear.
Okay. Sir, coordinator,
No doubt,
sir, shall we give maybe break for 5 minutes?
Yes, sir. Definitely, we can take a break for 5 minutes. We will join by 8:17 or now it is 8:12. Can we rejoin at 8:12, 8:17, sir, or 8:20?
Okay, 8:20. Then we'll close at 9:35 or 9:40. Okay, na?
Okay, sir.
Okay.
So there is a break for 5 minutes. We will rejoin at 8:20. Thank you.
Thank you.
Sir, can you share the PPT after this session?